lot of people missing, but there was really only 11.
I think they're still
Only
eating
11
turkeys.
missing?
Yeah.
Oh,
So
yeah.
far.
That's a lot.
That's okay. Well, I think people,
We don't need them.
yeah,
No, we don't.
people are kind of like, they're remembering, oh yeah, I had all this stuff to do, and stuff that was due. So I'm just going to skip class and do all the stuff that I had to do today that I should have been doing over break. That's usually what Monday after break is for, which is why I don't assign anything. We shall see.
Is game theory a part of discrete math?
It can be.
It can be.
Yes, absolutely. Unfortunately, we need a little bit more stuff to do that. Like for specifically game theory, you have to go through win-loss analysis, and that usually takes about a couple weeks just to teach that theory. So it really is discrete when it comes down to it. So yes, it can be. In fact, it is. Okay guys, so just a heads up as to what's going to go on. Today we're going to finish up our last two recursion problems, and then we're going to go ahead and start our last topic in the course, which is going to be graph theory. And then hopefully Wednesday we'll be able to finish up our graph theory stuff. Okay. Next Monday, what we're going to do is we're going to use that date to review for the final examination. Okay. And then what I'll do is I'll make assignment number 12, the last assignment, due next Wednesday as well. Assignment 11, which is what we're going to finish up today, that'll be due next time. Okay? If for some reason we get all the review stuff done on the 5th, then what you guys can do is you can just email me a copy of the assignment 12, and I'll just grade it that way, so you don't have to physically give me a copy. Our final is scheduled for the 14th, and because of the 3:15 class, it goes from 3:15 to 5:15 in this room. Okay? All right, so that's what's going on. Posted on Blackboard if you guys have any questions. All right, so any questions about anything, guys, before we get started? Okay. So a long time ago, we started this thing called recursion, and I wanted to finish up the recursion today. So one of the things that we learned how to do last time was we took something that was recursive and we wrote it in a linear form. Well, not linear necessarily, but we wrote it into like an indexable form, so that way you could just substitute a number directly and get to the answer. Okay, so that's what we're going to look at today to finish those up. The ones that we've looked at so far weren't so difficult. Okay, so we're going to look at more difficult ones today. So I want you guys to take a look at this recurrence relation that we have up here. So we have d sub k equals 4d sub k minus 1 plus 2. The initial value is 3, and k always has to be bigger than or equal to 1. Okay. You may or may not remember, but the way that we tried to be able to write something like this into a non-recursive form was we used the method of iteration. Okay? So we started by writing the first, the second, the third instance, and hopefully we saw a pattern. Okay? So let's go ahead and do that. Okay? Now d sub 0 is clearly equal to 3. D sub 1, all we're going to do is take the previous instance, plug it back in for d sub k minus 1, and then we have the 2 on there. So d sub 1 is going to be 4, quantity 3, plus 2. Right. Now we all know that equals 14, okay? But 14 doesn't necessarily help us out. Okay, in fact, I know it doesn't in this instance, okay? It might, you guys might think it does, but it doesn't. Okay? D sub 2. Okay. Now, if we think of it in the way that a computer would think of recursion, that might be the easiest way to start this, okay? So, D sub 2 is going to be 4 times the previous instance. The previous instance was 4 times 3 plus 2. And then we have another plus 2 as a result of this plus 2 that's out there, okay? So does everybody see what we're doing here? All we're doing is we're just plugging the previous instance back in whenever we see a d sub k minus 1. Okay, so this guy right here, that's substituted in there. All right. Now, a lot of us would look at that, we'd go through, we tried to simplify it, okay? And that's exactly what we're going to do, but the question is, how far do we simplify it, okay? So let me show you guys maybe 3 or 4 or 5 different ways that we can simplify this, okay? One way we can simplify it is just do 4 times 14 to get 56. 56 plus 2 is 58, okay? So one way we could write that as 58. Another way we could do this is write this as 4 times 14 plus 2, okay? Another way that we could write this is we could write this as 4 times 12 plus 4 times 2 plus 2, okay? Another way that we could write this, okay? All I'm doing is I'm just showing you guys different ways to write this, okay? Another way I could write this is 4 times 4, or 4 squared, times 3, plus 4 times 2, plus 2. Another way that I could write this, if I really wanted to, is I could just write this as 4 times, I guess I could just write this as 4 times 12 would be 48, plus 8, plus 2. Okay? So the question is, which of those ways is the best way to write this? Okay, there's 5 different ways, okay? And unfortunately, one of the things that we learned in recursion is that it's difficult to maybe pick the best right way. So let me ask you guys, which one do you think is maybe one of the best ways that we could write this?
4 squared 3 plus 4 times 2 plus 2, that way.
This guy? How come?
Because if you do this, then you can find that index, that square is like with the index. You can find a relation with that if you do
so
3 more.
maybe we might be able to find like a relationship between the index and maybe the exponent. Okay, that might work. Okay. Also, if we could try to write it in exponent form, it might be helpful for us. So I don't think 58 is going to help us too much, because who of us can see a pattern of 3, 14, 58, and then the next one after that? That's not going to be helpful. Okay. So I think out of all 5 of these, I think this one's going to be the most useful for us. Okay? If you don't believe me, just try some of the other ones. Okay? You might be convinced otherwise. Let's find d sub 3. Okay. So all we're going to do with d sub 3 is we're going to take the previous instance and we're going to substitute it back in to d sub k minus 1. So it's going to be 4 quantity, 4 squared times 3, plus 4 times 2, plus 2, plus 2. Okay. And just like we did in the previous, let's just distribute the 4, but keep it in the exponential form, as opposed to computing. Okay, so this is going to be equal to 4 to the 3rd times 3, plus 4 squared times 2, plus 4 times 2, plus 2. Okay. All right. And again, one of the most difficult things about recursion is just being able to see the patterns that are going on. Okay? And like I said, these are just 5 of a number of ways that we could have written that. Okay? I mean, if I wanted to, I could probably have written it in like 30 ways if I wanted to, but trying to show you guys the most efficient way. Okay? Let's just do 2 more iterations or 2 more instances, because then we might be able to see a pattern that's going on with this. Okay? So I'll just go over here. I'm going to write d sub 4. So d sub 4 is going to be equal to 4 times that instance. So 4 times the quantity of 4 cubed times 3, plus 4 squared times 2, plus 4 times 2, plus 2, and then another plus 2. And notice each time, guys, there's another plus 2 because of the plus 2 in the original recursive sequence. Okay? if I distribute, we wind up with 4 to the 4th times 3 plus 4 to the 3rd times 2 plus 4 squared times 2 plus 4 times 2 plus 2. And now maybe you guys are starting to see a pattern. Okay? In fact, one of the things that we notice is that there's descending order of exponents of power 4. Most of them have a coefficient of 2 along with it. Now there's this one oddball one with a 3 in it. Okay? If I was to ask you guys to make a guess about d sub 5, okay? Does somebody think they might know what the 5th instance looks like? So, James, go ahead.
4 to the 5th times 3
Okay.
plus 4 to the 4th times 2
Uh-huh.
plus 4 to the cube times 2
Uh-huh.
plus 4 squared times 2
Uh-huh.
plus 4 times 2 plus 2.
Sounds good to me. All right. So, let's hold on to that for a second, okay? Because we have, remember, the whole goal is to figure out what the nth iteration would look like. Okay, hopefully it wouldn't be recursive, okay, which it isn't for me. All right. Now, let me ask you guys this question. If I was to say, because remember, the whole goal is to figure out what maybe the nth iteration would look like that's non-recursive. Okay? So if I was to ask you guys what the nth iteration, and obviously we have a first, second, third, fourth, and fifth. Okay? Does somebody think they might know what the nth iteration would
4
look like?
to the power n
Okay, so
times
4 to the n, go ahead.
3 times 3
Okay.
plus 4 to the power n minus 1
Uh-huh.
times, what is it, n
2.
minus 2, yeah,
Okay.
plus 4 to the n minus 2
Uh-huh.
times 2
Okay.
plus 4 to the power n minus 1, 3, yeah, plus 2 times 2,
And that would just keep going on, right?
yep.
For how long? Forever until,
Plus 4 to the 1 times 2 plus
yeah, so 4 squared times 2 plus 4 times 2 plus 2.
2.
Okay, nice. Okay, I just wanted to write the last 3 of them. Okay, well that looks good. I mean, hey, at least it's not recursive. All right. Now the problem is that we're asked to write this into the closed form. Okay? Remember last time I gave you guys that worksheet with the special summations on it? Okay? Let's take a look at that. Because maybe there's something in there that might help us, hopefully. If it doesn't, then we might as well just quit this problem. Okay. And let's look maybe towards the bottom of that page. Okay. Do you guys see any formulas that might be helpful to be able to write something like
4
that?
to the power n minus plus 1, what is it?
Yeah, this guy, like maybe right here. Oh, yeah, you have packages of paper. Okay. Guys, doesn't this look like it might be helpful? Because don't we have like a 4 to the n and a 4 to the n minus 1 and a 4 to the n minus 2? So I think that might be really helpful to us after we doctor it up just a little bit. Okay? So what's one thing that we might do to be able to use this formula that might be maybe not so obvious, but we could do? I see a 2, 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 I see a 2. Could I factor a 2 out? So let's write it like this, maybe. 4 to the n times 3 plus 2 times the quantity now of 4 to the n minus 1 plus 4 to the n minus 2 plus 4 to the n minus 3 plus da-da-da plus 4 squared plus 4 plus 1. Okay. Which, correct me if I'm wrong, guys, doesn't that look exactly like this? Except, instead of the nth power, doesn't it start at the n minus 1?
1 power.
So wouldn't we just replace this n over here with n minus 1, since that starts at the n minus 1 power? Okay? So, what we can do is we can now rewrite this as 4n times 3. This guy's an oddball term, okay? No matter what, it just doesn't jive with the rest of them because it has a coefficient of 3 as opposed to 2. But all the other ones have coefficients of 2. So we could say plus 2 times the quantity of 4. Since this is n minus 1, instead of n plus 1, we're going to write n minus 1 plus 1. Okay. So all I did was I just plugged in n minus 1 right here. Because this starts at n minus 1, I just substitute minus 1 over 3. Okay. Now we're going to get to the initial conditions and all that stuff in a second. Okay. Does that make sense, guys, as to why we did that? Okay, this form is the closed form of this series right here. Okay, we could prove that by induction. In fact, I think that we did prove that by induction on one of your homework problems. Okay. All right. So now we're just going to do some algebra. We're going to tidy this up, and then we can do the initial conditions. Okay. So I'm going to go ahead and make that 4 to the n minus 1 over 3. So now we get that this is going to be equal to 4 to the n times 3 plus, now we have 2 quantity 4 to the n minus 1 over 3. Okay. We can still clean this up even more, okay? Because couldn't I distribute the 2 and separate this term into 2 separate terms just by breaking apart the fractions since we're dividing by a monomial? So we could write this as 4 to the n times 3 plus 2/3 times 4 to the n minus 2/3. So let me make sure everyone's okay with that. Okay. But does everybody see what I did there? Basically, I distributed 2 in the numerator, and then I split it up into 2 terms. Okay, so this term, or this fraction, just became those 2 terms.
Take 4 to the power n common.
Yeah, guys, there's common terms there, right? Don't we have 3 4 to the n's and 2/3 4 to the n's? So we could just play collect like terms. If I combine those, 3 plus 2/3, I believe, is going to be 11/3 times 4 to the n minus 2/3. Okay. So all I did there, guys, I just took 9/3 plus 2/3 to get 11/3. Okay? And that's probably the most simplistic, non-recursive form that I could get. I could factor out a 1/3 if I wanted to, but this is what I'm going to stick with. Okay? Now, unfortunately, this doesn't mean anything unless we have the correct initial value for this. Okay? So, obviously, n has to be an integer. But what value should n start with if we want to make sure that we get the correct initial condition? And just to remind you guys, okay, let's go back to the original problem. D sub 0 is equal to 3. Okay, so whatever we plug in, okay, we need to get to a 3 with this. Okay, so I think 0 might be it, right, guys?
4 to the power 0 is 1, yeah. 11/3 minus 2/3 is 1.
Yeah.
That's it.
So all we're going to do is we're going to start at 0. Okay? And the reason we start at 0 is because if we substitute 0 back in here, okay, here's how we check this.
Yep.
11/3 times 4 to the 0 minus 2/3. And that just becomes 11/3 minus 2/3, which is going to be 3. And that's good, because remember we said that the initial condition, D sub 0, should be equal to 3. All right, so,
If you do all that, you get to your closed form, but when you plug the initial condition, the 0 in, it doesn't work, then
change the
but
index.
1 does.
Yes,
You just
started
say n equals 1.
correct.
or
What you're
greater
doing
than
is you're
equal
just
to
looking for the initial value of the iterator, basically what you're trying to get to.
1. But they're always gonna, the n is greater than or equal to is always gonna be either the same as the initial condition or only one away from it?
One,
depending
right,
on
it
which way
should
you're
never
going?
be any more than one away from it. I mean, you could if you really wanted to, but that would be
But then
extremely.
you're skipping what one of them would, you're skipping a condition.
Yeah, well, basically, yeah, okay, or you just tried really, really hard to do a change of base or change of index if you would, which you don't wanna do with this. Okay? Alright. So guys, now, on a scale of 1 to 10, when it comes to taking recursion and putting it into, something that's easily indexable, this is like a 1.5 out of 2. Alright, out of 10, I guess. So out of 2, that'd be nice. So this guy's a really easy example of how to take something that's recursive and write it into something that you just do explicitly, okay? So if you want to make some real money, okay, in your life, and I'm talking like somewhere in like the $500,000 range, start doing like your 4s and 5s out of 10s, okay? But those are really, really tough. Those are like
Which
maybe,
one?
what's that?
Which
Like
one?
about a 5 or 10, a 5 out of 10.
Uh-huh.
That's where you really, really, really make some money doing that stuff. So, but this stuff's like baby stuff. This is stuff that you can do in like maybe an hour. The other ones probably take like 4 or 5 weeks to do or something like that. So yeah. So have fun with that if you want to. All right. So anyway, I'm going to show you guys one more example of this, very similar, so that way you guys can see the process. And again, with these types, we're going to be using these special forms of the closed summations. Okay. So we have our last sequence up here. We have e sub k, which I had before, but I erased unfortunately. So e sub k is going to be equal to 5 e sub k's minus 1, okay, minus 3. E sub naught is equal to 2, and we're saying that k should be bigger than or equal to 1. All right. This problem is actually very similar to the previous, okay? All we have to do is just make sure that we have the correct sort of iterations going with this, okay? And that we don't simplify too far, if you would, okay? So, we already know what e sub 0 is, or e sub naught is 2. E sub 1 should be very, very easy for us to compute. We just substitute 2 back in for e sub k minus 1. So this becomes 5 times 2 minus 3. Okay? We could write that as 7. I highly doubt that after maybe the 3rd or 4th iteration, any of us would see a pattern. Okay? E sub 2. 5 times the previous instance, so 5 quantity. 5 times 2 minus 3 minus another 3. So, everybody okay with how we did that, guys? All we did was we took 5 times 2 minus 3, plugged it back into the previous instance. Okay? Again, we could compute that. We could say 5 times 7 is going to be 35. 35 minus 3 is 32. That doesn't help us. Okay? I always suggest to people keep it in the exponential form. Okay, so let's write this as 5 squared times 2 minus 5 times 3 minus 3. Okay? And I believe that form is going to be much more useful to what we have with the formulas. Okay? Let's go ahead and maybe write the next 2 or 3 iterations, because I bet you after 2 or 3 of these, you guys are all going to see the pattern. Okay? E sub 3. That's 5 times the previous instance, 5 squared times 2, minus 5 times 3 minus 3. Okay, minus another 3. And then all we're going to do is we're just going to distribute the 5 to all 3 of those terms. Okay, so this is going to end up being 5 cubed times 2 minus 5 squared times 3 minus 5 times 3 minus 3. Okay? So I'll let you guys copy that down while I erase the other board, just so we could do like maybe 1 or 2 more of these instances. So I'm betting there's some of you guys that can probably guess what e sub 4 might be. Okay, so let's just write out e sub 4, let's write out e sub 5, just from what we think it's going to be. and then maybe what we can do is come up with some sort of closed form for this. So, does somebody want to take a guess and tell me what they think or know e sub 4 to be? Go ahead.
5 to the power 4
Uh-huh,
times 2
okay,
minus 5 cube
uh-huh,
times 3
okay.
minus 5 square times 2
Times
3 3 3.
Yep, times 3, that's okay.
3 minus 5 times
Uh-huh.
3
Uh-huh,
minus 3.
yep, good. And again, that's after you do your substitution and your simplification, okay? I'm assuming that you guys can start seeing the pattern here, okay? For the second iteration, you had a 5 squared times 2, and then 5 times 3. For the third iteration, you had 5 to the third. So basically, anything with a coefficient of 3 starts with 1 less than the index. Okay? I'm betting that if you guys were to go through and do e sub 5, I bet you most of you guys could write out e sub 5. Okay? E sub 5 is 5 to the 5th times 2, 5 to the 4th times 3, 5 to the 3rd times 3, minus 5 squared times 3, minus 5 times 3, minus 3. Okay. So my suggestion, guys, would be to write out maybe the first 5 iterations, because with 5, it's not too many that it's painful, but it's not too few that you don't see the pattern, okay? There's always that balance, like how much is enough. I always say like maybe the 5th or 6th iteration is perfectly fine. Okay, so everyone good with these, guys? Any questions so far about how we actually wrote out the iterations? Okay, so now we actually have to get to the closed form. Okay, that's a tough thing to do. Right, so let's now try to guess this for the e sub nth term. Okay, in other words, instead of guessing out to maybe the 77th term, let's think what might happen the 77th time. Okay? So, does anyone want to take a guess and tell me what they think or what they know e sub n might look like?
5 to the power n times 2.
Okay, so 5 to the n times 2, good.
Then you take minus, take the 3 common, or
We'll do that next, that's fine.
Okay.
But you're okay, Art, go ahead,
okay,
keep going.
5 to the power n minus 1
Uh-huh,
times 3.
yes sir.
Then n minus 2 times 3, n minus dot 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 up to
Right.
3.
Yeah, so basically, the coefficient 2 starts with 5 to the nth, and then the third, or the coefficients of 3, okay, are going to start with the 5 to the n minus 1. Instead of plus, I'm going to use minus, because I was going to put a plus there, but we can clearly see that all the terms are negative rather than positive, okay? So it's going to be minus 5 squared times 3, minus 5 times 3 minus 3. Alright, and then guys, just like in the previous problem, we factored something out. So what should we factor out, and where should we factor it out?
3,
Not just 3, but negative 3,
negative 3.
right? Because remember, we have special forms of summations, okay? Not negative versions of those, okay? So let's factor out a negative 3, but let's start right here. Obviously, this first term doesn't have a 3 that we can factor out, okay? So, e sub n is 5 to the n times 2. And then we have our minus 3, which we're going to factor out. And that's going to be a 5 to the n minus 1 plus 5 to the n minus 2 plus da-da-da plus 5 squared plus 5 plus 1.
It reminds me of Calc 2.
Yeah, it really does look like some of the series that you guys have seen in calculus too. Okay. All right, guys. At this point, it's almost obvious that what we have in parentheses is very, very, very close to what we have as the very last entry on that sheet with the closed form of summation. Except once again, we don't start at the nth power, we start at the n minus 1th power. Okay, so once again, when we substitute, because we have an n minus 1, we're going to rewrite this as 5 to the n times 2 minus 3. Now quantity, instead of 5n n plus 1, we're going to have 5 to the n minus 1 plus 1 minus 1 over 4. Okay, now we're gonna worry about the initial condition in a moment. Okay? But I wanna make sure that you guys are okay with that. Okay, so everybody see how we're substituting back in? Okay, if it was n minus 2, you just substitute n minus 2 back in there. Okay, it just depends on where the index starts and stops with this. Okay, now we're going to clean this up. Okay, so let's go ahead and do a little bit of algebra to clean it up. Okay, if we do so, we're going to distribute the -3, and we're also going to split it up into 2 terms. Okay, and when I say yeah, I mean this parenthesis here. So this is now going to become 5 to the n times 2 minus 3/4 5 to the n, and then plus 3/4. Notice we have a negative and a negative. 3 times -1 becomes the 3/4. So, is that okay with everybody, guys? Any questions about that, Doug?
Why don't you split that up in the fraction that in
Oh.
the previous step?
Right here or up here?
No, right there.
We could, okay? I just wanted to make sure that everybody sees like this right here, to make sure that it's obvious to go from this to this form right here, okay? And this is on that special summations worksheet that I gave out last time, okay? You should have that, but if you don't have some copy, okay.
Chris, shouldn't it be 3 over 4 instead of 3 to the fifth, or 3 over 5?
Yes, it should be, I'm sorry, I made a copy error there. Thanks, Chris. I was just making sure you're paying attention, that's all. Thanks, I appreciate it.
And now you can come on
Right, now we can collect like terms because we have a 5 to the n and a 5 to the n, okay? So we can rewrite the 2 as 8/4 if we wanted to. So, correct me if I'm wrong, guys, but I believe that if we combine 2 and -3/4, that would become 5/4 times 5 to the n plus 3/4. Okay. Because we could write 2 as 8 over 4. Okay. If I wanted to be even slicker than that, okay, couldn't I rewrite this as maybe 5 to the n plus 1 over 4 plus 3/4? Because notice in the numerator we have a 5, so that would be 5 to the first times 5 to the n. So we just have one more exponent of 5 that we're adding in there. So I think that might be the cleanest possible version that we could get of this in the most simplistic form. Okay? Although if you guys got to the last one, I certainly wouldn't knock off any points for that. Okay? But again, I want you guys to simplify it as much as possible, just so that way you guys can understand how that works. Okay? So this would be one of the most simplistic forms. In fact, I think it's the most simple form, because there's less stuff that you have to work with. Unfortunately, we have to make sure that we start the correct index with this. Okay? So,
Why wouldn't you just put the 5 to the n plus 1 plus 3 all over 4?
oh yeah, we sure could do that. Okay? Another way we could write this,
I mean, if you wanted the
Yeah.
simplest.
just one fraction. Yeah, we could do that. That's nice. It's 1 less 4 we have to write. Sure. Okay. I like that one better. 1 less 4 I have to write. So I'm going to double box this one. So I don't have to erase my box already. Although if you got to either the previous or the second to last step, either of those, that's perfectly fine too. Okay, it's like how much lipstick can you put on the pig? All right, but we still have to make sure though that we start at the correct initial value in this. Okay, so we're going to say that n is an integer. Okay. And then if you guys recall, let's see, maybe not. But we said that the initial value has to be 2. So whatever number we plug in for n had better start at 2 with this. So guys, it's either going to be 0, 1, -1, something like that. So did I figure out which one
Zero.
was? It's 0, isn't it, guys? Check out if you plug in 0. Okay? So n bigger than or equal to 0. If you guys plug in 0 here, 0 plus 1 is 1. 5 to the first is 5. 5 plus 3 is 8. 8 over 4 works out to be 2. Okay? So I just did it by inspection. Seems to work out pretty nicely. okay? I don't want you guys to assume that the domain of the recursive sequence is the same as the domain for the non-recursive sequence, or the closed form of this, okay? You can't make that assumption. In fact, we've already seen 2 instances today where that contradicts that already, okay? So you can't just start at 1, okay? You have to just go trial and error. Most of the time, it's either going to be like -1, 0, 1, or 2, something pretty basic, okay? All right, so these are the last couple problems, I believe, that are on assignment number 11. Okay, so any questions I can answer for you guys about being able to take the recursive types of sequences and being able to write them as closed forms? Okay. All right, make sure you guys are definitely using this sheet. Okay, you gotta make sure that you have this. If you don't have it, either I got a couple up here, or you guys can just get one offline. So that you guys make
Can
sure
I ask you a question on
Yes, sir, please.
assignment 11?
Yeah, go ahead.
On assignment 11 number 8,
Okay.
okay, I did this thing, but the answer I was getting, I'll show you after the class actually.
Yeah, why don't you show me after class, because it might be like one of those things that's, like you've got it down, and I don't want to say you're right or wrong with it.
Yeah, I mean, I think
But you will, right?
Oh, I will, oh, no, I'll tell you if you're right or wrong,
There you go.
at least what I think it is. I hope it is. Review. Next month, right. I'm going, so, I'll talk to you. I'll talk to you later, okay? No, that's okay, no. So let me wait. That's okay. Right, let me wait till everyone gets a copy, hopefully extra. Thanks.
Oh, thank you. You're welcome. Thank you, sir.
Thanks, John. All right. Okay, everybody get a copy of the final worksheet, at least for the course. Okay, so the last topic we're going to take a look at in the course is graph theory, and graph theory is a fairly easy topic, okay? Most of you guys are going to find this to be extremely simplistic compared to some of the other things that we've done so far. Okay, now I want you guys to take the concept of a graph that you have, and I want you to throw it away, okay? You guys think of a graph right now in Cartesian coordinates as the set of points that satisfies a one-to-one relationship. Okay, well that's a function, okay? Guys, the graphs that we're going to be looking at are completely different than that. I want you guys to think of a graph almost like a telephone and a bunch of wires hooked up to a telephone, okay? Like when you guys were kids, you guys probably remember playing like the game where you tie like a string to 2 cups or maybe even 2 or 3 cups. That's what a graph really is in graph theory, okay? So, when we talk about a graph, it's any geometric object comprised of 2 finite sets. There's a vertex set. Now, a vertex is not a point that satisfies a relationship, okay? So it's not like a scatter plot or a parabola or a conic or anything like that, okay? And then there's something called an edge set, okay? That's basically going to be the set of all edges that exist in a graph G, okay? So, let me give you guys just some examples of just some basic graphs, although you guys can see a graph down here. That's a graph, okay? Certainly not a function, and we probably couldn't be able to find some sort of equation to represent that, whether it be in Cartesian or cylindrical coordinates or whatever type of coordinate system. I don't think we'd be able to find a function to mirror that, okay? And that's okay, we don't have to. All right, guys, take a look at this very, very simplistic graph. Okay, this is the dumbbell graph, okay? This graph is the same as this graph, okay? So these 2 graphs are exactly the same. There's no difference between those 2 graphs in graph theory, okay? It would be the same as that graph. Okay? All 3 of these graphs are the same thing. It doesn't matter about the magnitude of the edge, okay? It doesn't matter about the positioning of the vertex or the positioning of the edges, okay? In graph theory, it's all the same, okay? So, guys, does that fundamentally make sense, guys? It doesn't really matter how long your wire is. It just matters that the 2 cups are connected to one another, if you would.
vertex are those circles?
Correct, this is a vertex. So I could call this like V1, and I could call that V2. And this might be called edge 1, or E sub 1, okay? Generally in graph theory, like we like to denote vertices by V's and W's, and we like to identify edges by like E's and D's, if you would. Okay, so like this would be V1, V sub 2, E sub 1. This would be V sub 1, V sub 2, and then this mess that looks like a 2-year-old grabbed a crayon and tried to construct the Statue of Liberty, that's E sub 1. Okay? All right. By the way, we're going to learn this a little bit later in the course, but these three graphs are isomorphic. Okay? Like you guys know what an isosceles triangle is, right, guys? Isosceles means two same. Iso meaning same. This means same shape. Isosceles. Or I'm sorry, isomorphic. Okay? Morph meaning shape. So these three graphs in graph theory are isomorphic to one another. We're going to take a look at that later in the course and how do we prove isomorphism. But for right now, I just want to make sure you guys understand. Okay, so this is really fundamental stuff. I'm just making sure everyone's on the same page. Some definitions for you guys. All right, anytime I talk about an edge that's connected to a vertex, I say that it is incident upon that vertex. Okay, so in other words, E1 is incident upon V1. E1 is incident upon V2. Okay, so that's what incident means. Okay, two edges are parallel if they have the same endpoints or the same starting and beginning and starting and ending vertices. So, like if I was to do this and call this E sub 2, E sub 1 and E sub 2 would be parallel to one another. Okay, now you guys think of parallel in mathematics meaning same slope, right? Same thing as like orthogonal, right? Or orthonormal, okay? By the way, what's the difference between orthogonal and orthonormal? Anybody know? Because they mean the same thing, right? They absolutely
Normal, yes, it has to be -1, right?
well, they both imply perpendicularity. One's a vector and one's a plane.
Gotcha.
So that's the only difference. So you guys have probably heard those terms before. One just means you're using a plane, a finite, I guess a finite plane. The other one's referencing a vector or an array that goes on forever. So. Yeah, so those terms are actually delegated very specifically for reasons. So, regardless. All right, same thing with adjacent vertices. All right, basically when you talk about a loop, it's the same thing as a loop as you guys would think about in real life. You have a vertex, you have an edge, it begins and ends on the same vertex. Okay, nice and easy. Simple graph, no loops, no parallel edges. Okay, basically there's almost like a one-to-one correspondence. Okay. You can only get from one vertex to another vertex by traversing an edge. Okay? A degree of a vertex basically is the number of edges that's incident upon that vertex. Okay? So it's really easy. If you can count the number of sticks that are going out of the vertex, that's the degree of it. Very easy. Degree of a graph is the sum of the degrees of the vertices. Okay? So you just add up all the vertices degrees, that's the vertex, or that's the graph's degree. Something called the handshaking theorem or the handshaking lemma basically says that every graph must have an even degree. Okay, you can't have an odd degree of a graph. Well, you can, but you'll just be wrong. Okay, there's no way to have a correct graph to where the degree is off.
Can you, that is the sum of the degrees of, what is the sum of the degrees of vertices? What does that mean?
Where at? Right here?
Yeah, this is the sum of the degrees of the vertices in G. The degree of a graph, what is the degree of a graph?
Oh, degree of a graph is just the degree of all the vertices. So you take the sum of each of the vertices, that's the degree of the graph.
I mean, like how many vertices are there, units?
No, let's say like in this graph right here. This has degree 2, right? This V1 has degree 2, because there's 2.
Oh, okay, 2, okay.
This has degree 2.
2, okay.
So this graph has degree 4. 2 plus 2 is degree 4.
Gotcha.
Okay, that's all the degree of a graph is. So you find the degree of each of the edges, or each of the vertices, you add them up, that's the degree of the graph.
Gotcha.
Okay, nice and easy. Okay. Guys, any questions about any of these definitions before we go through and just talk about some of the definitions for these? Okay, very, very easy stuff.
So like in that diagram, that A, point A has 3 degrees, right? 1, 2, 3.
A actually is
4.
Yeah. So degree A, in fact, we're going to look at that later, that it does have a degree of 4. Other questions, guys? Okay, let's just go ahead, bowl through these questions. We'll get to stuff that's a little bit harder. Okay, so letter A, I asked you if the graph G is simple. Guys, why would that graph not be simple? Has some parallel edges, right? Can't we just name a pair of parallel edges? Maybe like what, E5, E4. We also see that E7 and E8 are parallel, okay? Because they both begin and end on the same vertex, okay? So, no, we could say E5, E4 are parallel. Okay, in parentheses, all of them put. So are E7, E8. Okay. Easy, right guys? We can all do that.
One more thing, when you're saying loop is the one that you drew the third one, right?
No, sir. A loop is this.
Oh, okay, okay.
So this is V1, this is E1. Okay? One edge, one vertex. Okay, that's a loop.
Like a ring. Okay.
Yep. All right. If I wanted to find the vertex of set, in other words, V of G, okay? V of G is the set of all vertices, okay? So it's a set, so we're going to write it like a set notation. So all I have to do is just list out all the vertices, A, B, C, D, E. Okay, so that would be set A, B, C, D. Okay? Easy enough, right guys? We all know how to write the set of those. Okay? If I was to ask you guys for E of G, okay, that's not a function, that's the edge set of graph G. Okay? Wouldn't that be edge 1, edge 2, edge 3, edge 4, etc., all the way up to edge number 8, because there's 8 edges. So we could write this, oh, there's 9? Oh, there is an edge 9, if I could look at that. Sorry about that. Thank you. So that would be E sub 1, comma, E sub 2, comma, E sub 3. And then you guys could either write it out, or you could just do this, to where you denote the pattern. Okay? I don't care which way you guys do it. I highly doubt anyone's going to write out all 9 of those. Okay? As long as you establish a pattern and show that it works out, that's fine. Okay. Guys, any questions about a vertex set? Any questions about an edge set? Nice and easy, right guys? Okay. Name 2 parallel edges. C problem A, right guys? Didn't we already do that in part A? So no need to do it again. So C part A.
Can we do that on the exam?
Literally, it's right here, it says that these 2 are parallel edges.
Yeah, so
and
if
then I
that,
can refer
if there's a
back.
case like that
Sure.
on
Yeah,
or
I
even
don't have
on the
a problem with
homework,
that.
like, can we just do that?
Oh, yeah,
instead of
sure.
part A?
Yeah, I didn't ask it on the homework of the exam.
Oh,
Sure,
okay.
you can do that. But no, I don't have a problem with that. It's clearly defined. Okay. If I wanted to ask you what the degree of vertex C is, okay, so deg C, or degree of C. Guys, what is the degree of vertex C? 5, right? There's 5 edges that are incident upon it, okay? So, degree of C would be 5. Okay, everybody sees that, right guys? You can count 5 sticks coming out of it, that's easy. If I was to ask you what the degree of A was, in fact, didn't we already answer that a little bit earlier? The degree of vertex A would be equal to 4, because there's 4 edges that are incident upon it. Okay, by the way, it is possible for a vertex to have 0 degree. You can't have negative, and it has to be a whole number value. Okay.
Would it be 0 degree if you just like put the vertex
Yeah,
somewhere?
like for instance, if I had a graph that looked like this,
Right.
and this was V1, V2, V3.
Is V3 just like arbitrary in this case or something? Because like, does it actually have any significance if it's just kind
If you think of it like the example that I gave before where you have like cups to a string, that's just a cup lying out somewhere. It's still a cup. It's basically a computer that's not hooked up to any sort of connection, if you would. Okay? So those are 2 examples to where that you could see in real life that maybe these 2 computers are hooked up to a network. They can talk to each other. This one's not hooked up yet. It has the capability to be hooked up, but not quite yet. Okay? All right. Let's see, what do we want? Part F. Okay, we need the degree of the entire graph. Okay.
So never put vertex labeled G.
Correct, because then that's a redefinition of G, isn't it? Just like any other variable, you never want to define a variable twice, okay? Well, you don't want to if you can avoid it, okay? So, degree of graph G, okay, is going to be equal to, we know degree of A is 4, okay? B has degree of 3. We already said C has degree of 5. D has degree of 2, doesn't it, guys? And then E, I have to scroll up a little bit, sorry, has 4. Okay. So, does everybody understand what I did there? Like, I'm not just pulling numbers out of thin air. I just found the degree of each of the vertices. Okay, so this is degree A, degree B, C, D, E.
I don't understand what degree is.
Okay. How did I get? Okay, let me take a look at that. Okay. There are 1, 2, 3, 4 edges sticking out of it, right? That's how we get degree of A is 4. Okay. If we look at degree of C, 1, 2, 3, 4, 5. There are 5 edges sticking out of that vertex. That's how you find the degree of a vertex. What I did was, I did that for all 5 of those vertices. Okay? So if we add this up, 12 and 5 is 17, or sorry, 12 and 5 is 17, and 6, wait, what am I adding wrong? Is that,
18.
it's 18.
Yeah.
Yeah. Where's it going? Wait, 4 and 3 is 7. Oh, the whole degree, okay. Yeah, really. I don't know what I'm thinking. I don't know what I'm not thinking, but.
I have no idea what you were doing
You know what I was doing? I was doing 4 times 3 plus 5. That's what I was doing. Because I was getting 17 out of it. Okay. I need to stick to addition. Okay, does that make sense, guys? Any questions? Okay, that's the degree of the graph. And then finally, for G, it says to find all edges that are incident upon D and E. Now, when we say that, let's just make it 2 separate problems. So, incident upon E and, let's just put it, and incident upon E. Okay. So basically, incident on D, okay, that would just be a couple edges, right, guys? If we look at that, we have E1 and E2. Okay, so the only edges that are incident upon D are E sub 1 and E sub 2. Okay. And then if I say incident upon E, you said E has a degree of 4, so we should end up with 4 vertices.
E1, E3,
Yeah,
E4,
E1,
E5.
E3, E4, E5. Okay, so E1, E2, or no, wait, E3, right?
E3,
E1,
yeah.
E3, E4, E5. Thanks. Okay. So that's the essential terminology of a graph. Okay? So, Michelle?
If you had a graph of just roof, is that of a degree of 2 or it's not a graph?
Yes, that's a good question. Okay? The degree of this graph G would be 2. Every loop contributes 2 to the degree of it. Okay? Yeah, even though it's one edge, it still has like the 2 stems sticking out of it.
Oh, from the Bartius.
Yeah, right.
There's still 2 contact points.
Yeah, that's exactly right, or 2 exit points if you would. Okay, good question, Michelle, thank you, ma'am. All right, guys, any other questions I can answer about the basic terminology of graph theory? Okay, really, really easy stuff, right, guys? Okay, so what if I give you guys a scenario to where I ask you to be able to construct a tree, okay, or if it's not possible, to explain why. So let's take a look at some of those types of problems. All right. So, I have a graph, and I'll ask you guys to construct this. I have a graph of 3 vertices with degree 1, 2, and 3, okay? Now this is possible, okay? We'll take a look at maybe some that aren't possible later in the course, okay? So, if I want to have a graph with 3 vertices, degree 1, 2, and 3, I want you to notice I didn't say it had to be simple. I didn't say it had to be connected. I just said a graph, okay? So, when I say just a graph, you do whatever you want with this, okay? So couldn't I do this, guys? Couldn't I draw a vertex here? Draw a vertex here. draw, so that has 3.
You have to go off the first one.
Yeah, we have to go off the first one, like that. Okay. And I think that makes it really nice and easy, doesn't it, guys? Okay. Sometimes what students do is they look at it and they try to think of a simple graph that has to be connected, okay? Unless I specifically say it's simple and it's connected, you don't have to do it that way. Okay, does that make sense to everybody, guys? Any questions?
Oh, 1, 2, and 3, okay, separately, okay.
So this has your degree 1, this has your degree 2, and because of the loop, that has a degree of 3. Okay.
So,
Yeah. That thing that's stemming out is a loop.
so for B, you said they don't have to be simple or connected. You can
Oh,
just-
no. The first one I didn't say simple, right?
Mhm.
For letter B, it says it must be a simple graph. Okay, so that kind of narrows down the possibilities of what you have to work with. Okay, so for B, that one's a little bit tougher. Okay, what I usually do, guys, I just make a graph and I start out with the lowest degree and work my way up, because that way I can try to save the hardest stuff for last. Okay, so this might work. I don't know. So we try this. And then we need something with a 3 in there. So, and we need a 2. So, let's see, what do we think, guys?
Just make a triangle and then have one stick off and just be connected to another vertex.
Okay. Like this.
Yeah.
Kind of boring, but it works. Looks like a coat hanger. I mean, we're not going for artistic, I guess, integrity here.
So, you start with the easiest one. Why didn't you just draw the 0? Draw the.
Well, this one, I don't know. This
Oh,
one.
you're on beat. You're a beat.
Right.
Sorry, I'm a beat.
But that's okay. Yeah. So unfortunately for this one, I think this might be the only way to do it. I want you to notice though, this aren't parallel edges, okay? In other words, you have a vertex in between like these 2 edges, so it's not parallel necessarily. So this has degree 2, 2, 3, 1, which I believe is exactly what we look for. So thanks, John. Okay. Guys, any questions about that one? Okay. For letter C, we have 0, 2, 2, 2, 2, 3, 4. Okay. So I guess the easiest one to draw is the 0, right? So we start with that one. And then 2, 2, 2, 2, 3, 4. So did anyone get that one?
You just draw like a cube
Okay. So we can draw a cube.
and then have things stem off of that.
Okay. So let's try that. Okay. So that's our 2, 2, 2, 2 and our 0. Now it has degree 0. And then stem off of that.
Put one in the middle.
Yeah,
Put a
yeah.
dot in the dead middle and connect them.
So then you connect it with one of the corners,
Okay.
because that creates a 3. But
So that's a 3, and this is now a 1. Okay.
You don't need a one.
Right.
right.
I'm just doing what you guys told me to do.
Connect it with the 2, the other
So
3
this
dots.
2 right here?
If you connect it with the other 3 dots,
Okay.
would that become a 4?
Oh, yeah,
but
sure.
But then you'd have.
That's a
more-
4.
Yeah, then you
Oh,
can
That's
oh,
a 3.
then you
That's a
have
3.
3.
And that's a 3.
Oh, you're
So that doesn't work. It was getting too ugly. So, other suggestions?
Does it? Can you just make a line that sticks out and not connect to anything?
Oh no, you have to have it connected to a
Wouldn't that
vertex.
technically be a loop anyway?
What's that?
Wouldn't that be a loop? Just a line?
Yeah, if it's just a line, it has to, basically if you do this, that's by default, that's what that is. Okay, so yeah, if you just have a line, that's what that is. Scratch that out, line. That doesn't exist.
Don't they have a erase function?
They do, but I'm too lazy to pick it up.
So,
Can I get this one? Man, this is easy stuff, right? Yes, sir?
Draw the box first.
Okay, I just need that. I'll need it. You guys are bossy. Okay,
Extend one of those vertices to the right or something.
so like,
Yeah.
okay,
And then we become 1, 2, and from that vertex you can make it, try to do it 4 or something like that, extend them.
Or connect it to the top right dot, so then that also becomes 2, so then you have a 3 and a 2.
okay, so this,
So now you
Yeah.
have 4 2s and 1 3.
okay.
No, because that's a
The
three.
top left, you do the
So this is a three.
Oh. No. Instead of connecting it, draw a separate. I mean, like from the instead of connecting it.
We can't do this. Yeah, it's not.
8 plus
That's
3 is
odd.
11,
No.
11 plus 3 is 15, 15 is odd, can't be done. Remember handshaking went on?
You could have just.
Ah.
No, I couldn't do that.
I thought you said we would do that later in the course.
We did, 2 minutes later. Absolutely correct, Brian. I did not lie to you, okay? Not possible.
Wow, we got later in the course real fast.
Ah,
No, all the tests and classes got to like that.
you do?
That'd be nice.
What, not possible?
Yeah, so all we got to do is.
I don't know if you want that, trust me. Okay. All right, any questions, guys, about being able to construct the graphs, okay? Make sure you add them up first to ensure that they meet the handshaking theory. Okay, a couple other types of graphs are complete bipartite and complete graphs, okay? A complete graph, case of n, so if you see this case of n, that just means you have a complete graph. It's a simple graph to where each vertex is connected by exactly one edge, okay? So basically, what you can do is you can travel from any one vertex to any other vertex in one traversal, okay? The way I think of a complete graph is, I always go back to this example, like the cups, the telephone, where you have the cups and the wires. There's, like, every person in the class has one cup, and everybody can talk to everybody, no matter what, through one wire, okay? So that's basically the way you think of a complete graph. A complete bipartite graph, which if you have k, m, comma, n, simple graph with 2 sets of vertices, okay? You have a vertex set V's, and then you have a vertex set W, okay? Every vertex in V can go to every vertex in W in one traversal, okay? So if I want to go from V to W, I can get there in one traversal. I cannot go from V to V in one traversal. I can't go from W to W in any one traversal, okay? So basically, V's and W's are connected, V's are not connected, W's are not connected, okay? So that's what a complete bipartite graph is. I'll explain to you guys why you ever want to care about one of those in real life in a few moments, okay? Let's just go ahead and construct these complete
Oh, so you cannot
graphs.
connect from V to V, but you can connect from V to W?
You have to connect from V to
To
W,
W,
yes, okay? So V to W is okay, V to V is not okay, W to W is not okay,
Okay.
in one traversal, okay? You can get there in 2, but not 1, okay? All right, for letter A, K3, okay? That means I have 3 vertices. I can get to any one of those 3 vertices in one traversal, okay? So here's K3, pretty boring. Okay, that's what K3 looks like, okay? It's not difficult, but if I start on any vertex, I can go from one vertex to the next in one traversal. I want you to notice there are no parallel edges, there are no loops, okay? By the way, don't confuse a loop with a circuit. Loop means you begin and end on the same vertex in one traversal. Circuit means more than one traversal. We're going to learn about circuits next time, okay? If I was to construct K4, okay, if I drew this, I would be close to K4, but I wouldn't necessarily have it. Okay, so, can somebody tell me why that is not K4? What am I missing? Go ahead,
You
James.
go from corner to corner.
Yeah, the corners are missing, right, guys? So what we could do is we could just draw a crisscross. Now notice if I draw a crisscross through there, that doesn't create another vertex, okay? Another way you guys could do it is you could do this, right? If you wanted to avoid the crisscross. Because now what I could do is I could go from any one vertex to the next vertex, okay? By the way, traditionally, when I see K4, this is what K4 usually looks like, okay? This is just one way to draw it, or what I put up there. But usually, when I look in textbooks, in graph theory textbooks, it looks a lot better than that. But that's what K4 usually looks like, basically a pyramid, if you would, okay? It It's either that or the square, okay? And again, we talked about this term earlier, but these two graphs are isomorphic to one another, okay? We're gonna have to prove that next time. We're not gonna prove it this time. Okay. Does that make sense as to what a complete graph is, guys? One traversal, no loops, no parallel edges, nothing like that. Okay, simple graph. Okay. All right, guys, let's go ahead and finish up by talking about what K23 looks like. Now, this is a bipartite graph, okay? That means there's two vertices in set V, 3 vertices in set W. Okay, so here's what 2, 3 would look like. Here's my 2. There's my 3. So let's call this set V, and let's call this set W. Okay, so that's what I mean when I say there's a simple graph with vertices V1 through Vm, V1 through Vm. Okay, and all I'm going to do is say that any traversal in V to get to W can be done once. Okay, so that's what K23 would look like. Okay. I want you to notice that I can't move from V to V. In other words, I can't move from this vertex to this vertex in one traversal. I have to bounce to somewhere in W to get back to V. Okay, so the only way that I can go from this vertex to this vertex is to go from here to another vertex and then back. Okay? Same thing with W, right, guys? I can't go from W to W in one move. Okay, Ryan?
So the rule is, like, you don't have to worry about what's in the set itself, but all nodes in the left set have to connect to all nodes in the right.
That's exactly right. Exactly one time. Okay? And that's what complete bipartite means.
But I thought V only can have 2 edges, right?
Oh no! V can have as many as it wants. It can only have 2 vertices.
Oh, vertices, okay.
Right. It can have 100 edges if it wants to, or if it
Okay.
needs to. Okay, does that make sense?
Uh-huh, okay, yeah, I got it.
Okay.
Can you explain again the whole concept of just having it only connect to the other side once? Like,
That, well, that's the whole definition of what it is.
Right.
Okay? Complete bipartite means that you can't move from V to V in one move. You have to make it in 2.
There's no
Same thing with
edge between
W's.
V to V.
Okay? You should not ever have this.
Okay.
Okay, that shouldn't exist. If it does, then it's not complete bipartite anymore. And guys, think of what bipartite means. It means 2 sets, and partite means separated. In other words, it's been a portion. Okay, that's essentially what we have right here. Okay? By the way, guys, in real life, this is an example of a password system. Okay, generally what happens is with a password system is that you have a computer. You want to be able to access something else. So you have to go through essentially a firewall. So in other words, there's going to be some sort of cloud that houses all the passwords. So you type in your password, this checks it, and then you're able to access something out. This is a fundamental data structure for encryption, if you would. Okay. Now, most of them are much, much more sophisticated than that. But I just want to make sure that you guys understand that this does have real life aspects. Just like this would. Like if you had a room full of computers, you would only want each computer hooked up to each computer once. You wouldn't want to have the same computer hooked up twice. It doesn't make any sense, okay? So, and I like the word that you were using before, nodes, which is generally how we use it in computer terminology. So if that helps you guys to think of it easier, that's fine too. Okay? All right, so any questions about complete graphs, guys? Really easy to kind of construct, not meant to be difficult. Okay. So make sure that you guys complete, I think it's assignment number 11. Okay, make sure you guys have that for me next time. I do have your guys' examinations and homework to give back. I'm ending a little bit early, so I'll give it back. So let me give those back to you guys. And if you guys have some questions for me, let me know. Once you get your homework and your exam back, you're welcome to leave. I didn't post these on Blackboard, but I did great. So sorry about that. I didn't make you wait for it. Okay. Thank you.
Thank you.
You're welcome.